All right. Hello and welcome to the EnergyTech University Prize regional competition. So we are so excited to have you here to hear your business presentations today. As I'm going to talk about in just a minute, EnergyTech University Prize is directly in line with the mission of the Scott Institute for Energy Innovation here at CMU. So we're so glad that you're here all competing for this prize. Now, as you know, EnergyTech Up, in partnership with the American-Made Challenges, is designed to be approachable, equitable, and scalable nationwide. And winners will be chosen based on the strength of their business proposal. So best of luck to everyone here. Next slide, please. So this is just a quick slide to show you my name, how to get in touch. We're on LinkedIn. We're on Twitter, and if you want to get in touch with someone, myself or anybody else on the team, just email that email address and we will all get it. Next slide, please. So yeah, as I was saying, the Scott Institute is Carnegie Mellon's energy research hub on campus with over 160 different researchers all across campus in engineering, public policy, chemistry, physics, you name it, because energy is such a complex problem. And at the end of the day, all we really care about is enabling a sustainable low carbon future through events, through collaborative research, through public policy outreach, et cetera. At the end of the day, what we really care about is making sure that this clean energy transition happens, it's sustainable, et cetera. And events like EnergyTech Up are directly in line with that mission, because the businesses that you guys are proposing today could potentially turn into real businesses that have real impact on the world and enable a sustainable low carbon future. So again, thank you all for being here. Next slide, please. And so part of what the Scott Institute does is we put on a bunch of events, this one included. This is our CMU Energy Week. It's happening next month, March 21st through the 24th. We're bringing together experts from all over the country to come and kind of put our heads together around the big topic of industrial decarbonization. So that's our big our theme this year and what we're going to be focusing the dialogue around. If you're interested, it's free, it's open to the public, anybody can attend, it's fully in person. So if you're interested in learning more or registering, please scan that QR code that's right there. We hope to see you next month. Next slide, please. So first of all, I just want to say a big thanks to our judges. They are going to be offering really invaluable feedback after each of your presentations. And asking good questions, and of course, ultimately choosing a winner to advance to the final competition. I'm going to spend a little bit of time reading their bios for each of you, and you know, it's kind of a lot, but I want everyone in the audience to really understand that not only could these be your future employers, but this is you. This could be you in the future, and so I think outlining kind of their career trajectory is useful for those in the audience. So. First off, we have Kristina Nikiforova. She's spent more than a decade in the energy industry, spanning engineering, consulting, startups, and utilities. In the early part of her career, she consulted at Accenture and then spent 6 years as an environmental permitting project manager focused on the siting, design, and construction of a large Federal Energy Regulatory Commission regulated energy infrastructure projects. She then went on to work for the Scott Institute for Energy Innovation and the Tech Transfer Office at CMU while getting her MBA, where she consulted energy startups spinning out of the university on technology, commercialization, and business strategy. Kristina is currently part of a Future of Heat team at National Grid, a utility based in the Northeast and the UK, where she works to transform the gas business through new ventures in renewable natural gas, hydrogen, targeted electrification, and networked geothermal. Previously, she developed electric vehicle charging and Future of Heat workforce strategy as an internal consultant for the utility. She holds an MBA from CMU, an MPA from the University of Pittsburgh, and a bachelor's in international relations from SUNY Geneseo. I'm sorry, I don't know how to pronounce that. Apologies. So that is Kristina. Next, we have Purna Majumdar. She's based in New York City and works for PEI Global Partners, a boutique investment bank focused on renewable asset transactions. She specializes in power markets and is in the process of honing skills in energy finance. So prior to PEI, Purna was an associate at ICF, where she worked with an advisory team focusing on Texas and California markets. And additionally, Purna has worked in India's solar PV industry and completed a master's degree in energy, science, technology, and policy at Carnegie Mellon. They are just down the hall from me, where her coursework included studies on power systems, data analytics, and machine learning. So that is Purna. Next, we have Tim Lee. He is part of the Walt Disney Company's corporate social responsibility, where he focuses achieving the environmental goals of net zero greenhouse gas emissions and 100% zero carbon electricity. His experiences include carbon accounting, renewable energy strategy, public policy, and he has a BS in electrical engineering from the University of California, San Diego, and a master's in environmental engineering from Carnegie Mellon University, my alma mater department, and is a fellow with the Clean Energy Leadership Institute. So that is Tim. And then last but not least, we have Stephen Euler. He's a compliance and operations professional in the energy industry. Mr. Euler has held roles of increasing responsibility from General Electric to Eaton to Westinghouse Electric, and his current role at Sea Power Energy. His roles have spanned finance and accounting, M&A, risk, and compliance with a breadth of education across stellar programs, including 2 at Carnegie Mellon. So that is Stephen. And again, I just want to say thank you so much to our judges. This competition would not be possible without you. And I really look forward to hearing the feedback that you have for all of our teams. And I'm sure all of our teams are very eager to hear your feedback as well. Next slide. So this is our team. A huge thanks to both Caitlin Haas-Conrad, Kristen Whitlinger, and Sarah Passerini. And without them, this event would absolutely not be possible without them. So you're going to be seeing a lot of Caitlin. She's going to kind of take over from here. But again, I just want to say to all the teams and the judges and those in the audience who are watching, thank you so much for being here. I'm so excited to see what happens next.
Hello, everyone. My name is Caitlin Haas-Conrad. I'm the Assistant Director for Partnerships here at the Scott Institute. I am going to be the MC announcer for today's competition. So first, I'm going to go through the rules. Each team is going to have 7 minutes to present. The start and end of each presentation will be announced by myself. We recommend that you keep a timer going on your end, maybe on a cell phone, because I am not going to give you a 1 minute warning, 30-second. I will just tell you when the 7 minutes is over so that I don't interrupt the flow of your presentation. It will begin. I will tell you when the 7 minutes starts at when it is over. After each presentation, you'll be getting 3 minutes to have the judges ask you questions and that you are able to answer. And then we will have 1 minute in between each presentation and Q&A session. At the end of the Q&A session, there'll be 1 minute for us to transition to the next team. During that minute, I will tell the next team, please share your presentation, and then I will tell you when your 7 minutes begins. Unless you are presenting or speaking, please keep your mic muted and your video off. Next slide. Oh, great. Okay, so this is the order of the 12 teams that are presenting today. If any of the teams have technical difficulties and drop out, your team will go next. So while this is the planned order, things could change as the competition goes on, but we will announce after each team which team is next. So just be waiting and be ready to hear your team's name so that you will know when to share your screen. And I just want to let everybody know that after team 7, we are going to have a 5-minute break where you can use the restroom or grab a glass of water. So we will be taking a break after the 7th presentation. And I think we are ready to go. So the first team today is Power 3D printed batteries with team members Alex Sanchez and Zahir Imam. If you can please, I will stop sharing my video. Okay, great.
Hello. Okay.
When
Can
you
you see everything all right?
Yep.
All right.
You can go now.
Great. Okay. Thank you, Caitlin. Thank you, judges. So anyone who's had a phone or a laptop die in the middle of their day knows that today's batteries have a lot of room for improvement. Hello, everyone. I'm Zahir and here with Alex. We are graduate students from Carnegie Mellon University here today to present to you Power 3D. So the problem we're tackling today is that modern batteries simply are not good enough for future use cases. Most of us with phones would love to not have a charge at the end of every day, and as technology continues to advance, current batteries will not meet future needs. Moreover, getting material that is reliably available, ethically sourced, and affordable is an ever-increasing challenge. So I'll briefly go over 4 main pain points when it comes to batteries. The first here is that batteries are only available in set standard shapes, which can be limiting for some use cases. Secondly, while there have been improvements to modern charging speeds, there is an increase in demand for even faster charging when it comes to some such cases as EVs. Thirdly, batteries are expected to last over 400 cycles before any sort of performance loss. And finally, improvements to standard lithium batteries is plateauing, meaning without radical development, there's not much more that can be done to improve how much we get out of the standard batteries we use. We believe we have a solution that addresses all of these pain points.
So at Power 3D, we're using a 3D printing process to print battery electrodes. 3D printing gives us a lot of flexibility on the shape and structure of the electrodes, which can enable some really unique designs. Printing allows us to create ultra-thick electrodes, which until now have been a technical challenge to create without performance loss. With these type of electrodes, we can use less components, we can charge quickly, and we have a longer cycle life performance. Our scalable process uses aerosol jet 3D printing, which aerosolizes a slurry of electrode material and deposits that slurry through a small nozzle. This results in some intricate lattice structures that have a high degree of precision and control. With these structures, we can address the pain points that we previously discussed. So we see better energy density, better specific capacity, and better charge rate capability. We plan to commercialize this technology as a battery cell supplier who designs and produces cells to our customers' specifications. These batteries could be used in a range of markets from medical devices to electric vehicles, but based on our preliminary customer discovery and some initial conversations, we believe our target markets are consumer electronics and wearables. These markets have market caps of hundreds of billions of dollars, and there's demand for batteries that are more energy dense and charge faster. The ecosystem for battery development is a very complicated network of suppliers and equipment manufacturers. The equipment manufacturers have rigorous processes to validate their technologies. So this means depending on the customer and the market we go to, we could either be selling components of batteries, fully constructed cells, or even potentially battery packs. So even though our battery may be at a premium because of the manufacturing process, we've learned that customers are actually willing to pay those premiums in certain cases if their performance needs are met. For example, we talked to a former engineer at Apple who said that Apple paid 4 times more for the CAN battery that's used in some of their Apple Watches compared to what they were using before in order to get the same level of performance. We also did a process-based cost model. So we looked at how the process would scale and what the potential cost per unit would be. And we found that costs could be between $20 and $35 for the size of a battery for wireless headphones. So while this is more than a traditional battery, again, we do see that people are willing to pay that premium. And we expect the cost to be driven down significantly by the print speed and number of print heads. So if we can bring that print speed up from 1 millimeter per second, which we've tested in the lab, up to 10 millimeters per second, which is only a fraction of what the machine is actually capable of, we could bring the cost down to $8 per battery.
So here we've segmented our competition into 3 main categories. These competitors all have different approaches to improving battery performance. We believe Power 3D can match or exceed the performance of all of these competitors. Our process is flexible with the materials we use and doesn't require developing new, unproven material, while still getting the same performance bump that these other competitors have been able to get. Not many companies are currently investing in 3D printing, and our understanding of this process industry will help us develop quickly while maintaining a barrier to entry. Great. So yeah, here are some substantial social and environmental impacts from this technology. On the sustainability side, better batteries means longer device life cycles, where people hold on to the devices longer. This results in less overall e-waste and fewer battery replacements. In regards to the energy transition, we believe as EVs become more popular, having better batteries will result in longer vehicle lifespans.
So to date, we have developed a proof of concept coin cell to show that this technology does work. We're currently doing customer discovery with the NSF I-Core program in order to better understand what customers really need. And that's a critical path. The critical path is to integrate those needs into a prototype and then work with the partner to validate that technology. The customer validation is a key activity because in order to gain customers, because like I mentioned previously, people really care about testing the battery in their use cases. So as we improve the technology, we'll be working on ways to speed up and scale the process with the goal of eventually reaching the EV market. So with the money that we are trying to raise right now, that will mainly go towards prototyping efforts. These metrics on the slide here reflect what we hope to achieve over the next 1.5 to 2 years as we look to improve battery performance and scale. So any initial funds that we get will be going towards hiring an additional engineer to develop and build some of these electrodes and then also test them in electrochemical testing. This competition could absolutely help with that process.
Here's a quick look at our 2-year plan. The main points I'll highlight for you are prototype development beginning.
Hi, Power 3D. Your
Yep.
7 minutes are up, but hopefully if there's anything you didn't cover, the judges will be able to ask you questions about it in the Q&A.
I think we got most of this.
Yep.
So thank you.
Thanks so much.
Awesome. Judges, please feel free to unmute and show your videos and begin to ask questions for the next 3 minutes.
Hi, Power 3D. Just a quick question on energy density and what you've been able to model so far, and then what kind of improvements you might expect over the next, say, 1 year or some volume type of calibration there.
Sure. Yeah, so we have this slide. We have this slide in our backups for these questions. But so with energy density, we've shown we can get up to around 300, 350 for some of our models. We need to test that with different materials still. So that's one of our biggest things. We've proven this out with like a silver, which isn't ideal for batteries, but we can expand this. Like I mentioned, this is material agnostic. So this can be expanded to new materials, traditional materials, and with some slight reformulations to the chemistry. Did that answer your question?
It did, and then I think in parallel, it may be a question on the volume of cycles expected, maybe by material type or as you move forward. I saw 400 reference, but I'm sure different use cases would have much lower or much higher assumptions baked in.
Yeah, so that's one of the big tests we still need to extend. I think we've tested up to 500, but we haven't gotten to like the 1,000 cycle test range yet. I don't believe I have that in here, but the performance is a much slower decline over that cycle life. It's about, I think, a 40% improvement over the cycle life compared to traditional manufacturing.
Oh, yeah. Can you go back to your slide on your market opportunities, like the large scale, small scale, like EV versus wearables and such?
Sure.
Do you feel your technology can also be applied to very large scale, let's say like a utility sized battery system for like generation transmission purposes?
Right. The key there is going to be scale, getting the process up to scale, because with grid energy storage, energy density is typically less important, and that's really where our benefit is. And so that's why electric vehicles would be a good fit. But with grid scale, you have typically more space to deal with. You can kind of have these bulky batteries that don't necessarily need to be small or large, but it might be good for, instead of like utility scale, but more for like a building or a house. But again, we need to get the production scale to that level, because those typically are bigger batteries too. So going from a headphone size to a house size battery is will take a lot of development for the scale up.
Thank you.
Okay, thank you. That ends our Q&A. Judges, please remember to submit your Google form at this time with the scores. And over the next minute, Kelly Energy Innovation, please turn on your cameras and begin to share your presentation, and I will let you know when to begin.
All right, while we're waiting, I have a joke for you. What do appliances dress up as for Halloween? The answer is energy vampires.
Great. The judging 1 minute is done. Aeromine or Kelly Energy Innovation, you may begin.
Perfect. Hello, everyone. Thank you so much for being here. We're excited to present to you our commercialization plan for Aeromine, the future of distributed energy production. So we are Alex, Anusha, and Aniket. We're a group of passionate and part-time MBA students at the Kelley School of Business at IU. We hail from 3 different states in 3 different time zones and come from backgrounds in corporate tech, software engineering, project management. Okay, according to a report published by the International Energy Agency, operation of buildings around the world consume 30% of the global energy and contributed to 27% of total energy sector emissions. Commercial and industrial buildings contribute heavily to this energy consumption and carbon emissions. A deeper look at the energy consumption profile of commercial buildings shows that electricity amounted to 60% of total energy consumption, and 84% of total energy expenditure are attributed to these large-scale buildings. Oh, apologies. Referencing the CBEC survey above, we segmented the commercial building electricity usage into 3 different categories: small, medium, and large buildings, as shown. The data shows that large buildings defined as 100,000 square foot and above, although just 2% of the total number of commercial structures, consume nearly 39% of the total energy in commercial buildings as a whole. This presents nearly a $46 billion opportunity to advance clean energy technologies. So these large buildings and their parent corporations are looking for new solutions to reduce dependence on an aging grid, and while significantly reducing their carbon footprint to realize their 2050 net zero visions. We propose tapping into the growing market of distributed energy resources, or DERs. DERs are small-scale green energy sources situated near the site of electricity usage. This proximity significantly improves robustness against grid outages, drives giant leaps towards decarbonization, and are arguably more economic over the long term. Moreover, DERs present a unique opportunity towards creating a new model for electricity markets where a better grid stands to gain significantly. We evaluated 3 growing DER solutions for power density, durability, costs, aesthetics, noise, and overall scalability. As evident, there isn't a single solution that's a winner in every single category. This led us to discover AeroMine. AeroMine is a motionless wind energy harvester for rooftops. When integrated with traditional solar, it matches the power output of the microgrids. It has a lower life cycle cost, greater durability, is easy on the eyes, and is highly scalable. AeroMine, or motionless integrated extraction, is a patented modular bladeless system that captures and amplifies airflow owing to its unique aerodynamic design, making it effective even in very low wind conditions. Developed by Texas Tech professor and longtime wind power expert Carson Westergaard, AeroMine is a revolution in distributed energy generation and has the opportunity to bring powerful, cost-effective, and durable energy generation capabilities in a variety of commercial uses. The AeroMine unit stands approximately 10 feet tall and can be installed permanently on flat roof buildings or fully mobile in a lightweight version, which is still being tested. So a bit of background about how it actually works. Make sure I move that. So the AeroMine wind power generation device is constructed without external moving parts and leverages aerodynamics to channel airflow past its race car-like vertically mounted airfoils, creating a low pressure area internally. The device's central tower feeds the suction from this low pressure area through internal pipework and past a small turbine in the base of the unit, which generates localized electricity. A typical AeroMine installation will consist of 20 to 40 units, each with a power rating of 5 kilowatts. Given the market opportunity in commercial building sector and AeroMine's suitability for large flat rooftops, we have identified 3 target building types for our first phase: warehouses and distribution centers, data centers, and malls and supermarkets. We've created a sample ROI calculation for a prospective commercial customer, and I do say sample. With additional time, we would have created a full ROI projection for the full term of the project, but we created this simple version with some basic assumptions. We assumed a 200,000 square foot warehouse facility requiring 40 AeroMine units. Given that the AeroMine is constructed without external facing blades, we've assumed an ongoing annual maintenance cost of approximately 1% of product value, which is low for the industry. This calculation accounts for the potential offset of energy consumption based on a cost of 14.8 cents per megawatt hour produced, and does not include some of the additional benefits such as the production tax credit or net metering potential. And happy to bring this up later on in the Q&A. Here are some key activities and resources that will be central to AeroMine's growth strategy. Manufacturing capability will rely on a strong portfolio of production assets, including machinery and a large-scale production facility and healthy vendor network. A direct sales organization combined with delivery and service infrastructure will enable and ensure that installations are effective throughout their entire lifetime. Key patents and IP will bolster AeroMine's position as a market leader, while expert management of capital will be required to allocate funds to appropriate projects. We expect the AeroMine module sales to be our primary stream of revenue. We also expect secondary revenue streams from auxiliary sales, such as storage systems, inverters, and others. Our business model will have a services unit generating revenues from integration with existing solar setups and long-term maintenance contracts. Though not a full assessment of AeroMine's costing, their general cost strategy and structure is as follows. Economies of scale will enable AeroMine to reduce variable production costs, negotiate better rates with suppliers, and reduce waste. Capital expenditures will be dedicated to high growth potential projects, including the purchase or construction of the original production facility, acquisition and maintenance of delivery assets, and other capacity expanding projects. And finally, attracting top talent will be a major cost center, though this is pivotal to maintain AeroMine's tech leadership position. A brief discussion of our success timeline. We will invest the next 2 years in prototyping and testing the AeroMine system in a variety of use cases. In parallel, we will seek to raise seed funding to support initial production, marketing, and sales expenses. In that next section, from 25 to 27, we will have identified our pilot partner, such as a warehousing or data center type of use case.
Hi, Alex. Your 7 minutes is up. Judges, please turn on your cameras and unmute and go ahead and ask some questions for the next 3 minutes.
Just a quick one on testing. What has been covered to date to, I guess, provide some confidence to put that to scale and schedule?
Sure.
I
There was
can take-
a medium scale, so independent testing conducted at the university level at Texas Tech on the efficacy of the device itself. We also have a case study, medium scale project that was done at a warehouse, I believe, in central Germany. EnergyTech, correct me if I'm wrong.
Yeah,
of
there's
being
a use case validation work going on currently at BASF in Detroit, Michigan as well.
Detroit.
There are 2 or 3 different places where we are, validating the feasibility of this technology.
Can you dive a little bit more into kind of comparisons between, so like, if I have a big warehouse, why would I choose this over solar? Just, you can go back to that slide, just kind of go through that a little bit more.
Certainly. So our recommendation and the way that it's been applied, previously in some of these test cases is actually in direct conjunction with solar arrays, where we've been able to, the AeroMind team has been able to mock up situations where we're able to offset over 100% of a particular facility's energy consumption needs. So major differences between the AeroMind unit and the traditional wind turbine. All of the components are constructed internally. There are no external facing blades, so that reduces the risk of any environmental interference, natural disaster kind of risk mitigation. When it comes to solar panels as well, that these only take up approximately 4 to 8% of the total surface area of a flat roof building, where solar panels may need to be applied to over 85% of the building to capture the same amount of energy. So they're highly efficient, highly safe, and very easy to install, and as well as being silent. Yep.
Just to add to it, AeroMind can also operate in cloudy and dark conditions when solar panels cannot.
Okay, thank you very much. That ends the Q&A for Kelly Energy Innovation. Judges, please submit your forms over the next minute. And Smart Material Lab, please share your camera and your presentation. And I will let you know when we begin the time.
Okay. Can you see my screen?
Yes, we can see your screen.
Yep. Hello, everyone. My name is Mohammed Purshans. I'm a PhD student at University of Toledo. We modified just a little bit the title and the team name, but it's not updated to the it will update it at future. So we will have a new member on the different major like the business law and environmental science as well, but it will join us shortly by maybe next month. If I want to go to the project, actually, oops. The controlling the temperature ratio is one of the challenge of the electronic device, and we try to use the PCM phase change material to buy somehow time to stop hitting the maximum temperature of this controller system. For achieving this aim, we try to simplify the test setup. And as you can see, we made an NiTi as a phase change material and combined with a high conductive material like copper and made it very simply by sheets. And then we try to control the temperature of the base. And as you can see, as a result, in NiTi copper sandwich, we will have more time to achieve, for example, to 120 C as a critical temperature. So in this figure, you can see even we have the copper or NiTi, it will hit the maximum temperature very faster than NiTi and copper. And in the future, the actual next step, we are working to optimize and increasing the contact surface between the copper and NiTi with additive manufacturing.
Okay. And now we'll talk a little bit about the available market for phase change material. The global market for this type of material is continuously increasing, and it's estimated that it will yield up to $4.4 billion by the year of 2026. The growth rate in terms of region is also growing, and as we can see in the map, United States is the interest in this manufacturing of this material is also growing in the United States. In terms of application, there are a variety types of application for this material, as we can see in electronics, in textile, in packaging, and so many other end user markets.
For this specific PCM, solid to solid, we will have two major actually fields of applications, from energy storage and also temperature overshoot controller. Potential market for this specific device could be transportation, batteries, and electronics. And for this time, actually, we choose the cooling devices for electronic boards or equipment as a target market. But as I mentioned before, one of the most important benefit of this material is energy saving that could be combined in the same time for temperature overshoot controller and also sometimes energy storage as well, depend on the specific application that we go through.
Our advantage is in the manufacturing of this type of material. Utiligo team is a leader in the IT manufacturing of phase change materials, and we started our work in 2015. And our citation records show that our published results have been referencing in international journals ever since, and it continues to be cited and referenced. Our work is we have done some comprehensive studies on these type of materials, but the aim of this presentation, we try to focus mostly on the application and the end user market in order to define some potential markets for phase change material in different applications, but specifically in electronic devices, to be able to work more on our technology and actually reaching to a point of the business and marketing. So thank you everyone for your attention, and please let us know if you have any questions or comments for us.
Thank you very much. Judges, you can now share your cameras and unmute to ask 3 minutes of question and answer.
Can you talk a little bit about your potential competition? About your competitors in the market? You know, what are other folks working on?
I think There is two types of competitors. The first one is in terms of the manufacturing. There are some conventional fabrication methods and additive manufacturing methods. And there are some advantages of additive manufacturing. There are some general advantages of additive manufacturing and some specific to face shield materials. And the other field of competitors is in terms of the material that we use. We are introducing phase change material NITI as a phase change material to be able to increase the latent in the figure that we discussed in the, I believe it was the second slide.
Thanks.
Hey, I have a follow-up question to that. So could you dive a little bit deeper into the manufacturing or the CapEx costs involved in this, and how exactly would you, what scale would you have to manufacture this to be cost competitive in the market?
The scale of the market, you mean, or the scale of the application, the size of application? You mean?
I meant it in terms of like to be competing with the other products in the market, and if you have to, you know, optimize your costs to do that, what scale of manufacturing would you require for this?
I think it depends on the funding that we can gain from the partner. Maybe we need, because as we show you this test setup, we are in the primary stage of working on our technology. So maybe we need 8 to 12 months of research and development. And for that,
based on the application as well and the scale of the market, yeah. Actually, our lab has a capability to R&D in the additive manufacturing with different type of technology, and so our partner could be actually in the as an end user or as a manufacturer side. So it depends on the partner. Then we could define, okay, what kind of actually collaborate we could have together, and then based on the size of the market, yes, yeah, we need to figure out how much actually found do we need.
Okay, makes sense. Thank you.
Thank you.
Thank you. That ends the Q&A period. We will now have a minute for the judges to deliberate, or not deliberate, to fill out your forms. And I will cue UC Powerhouse when it is time for you to start presenting, but you can turn on your cameras and share your screen now.
Okay. Okay. Do you see my screen?
Yes, we can see your screen. I'll let you know when we're ready to start.
Okay, thank you.
As we're giving the judges a little bit more time, I'll tell you another joke. Why did the tree install solar panels? It wanted to be a power plant.
Okay, team UC Powerhouse, you may begin.
Okay, so again, you see my screen. So hello, everyone. My name is Ahmed Al-Gohari. I'm a PhD student, and my team is Hussein, is undergrad student, and Professor Shaban Abdullah, the team captain from University of Cincinnati Aerospace Engineering Department, and we are UC Powerhouse team. So I'm gonna present our idea for the next generation renewable energy turbine power plant. So who we are? We are University of Cincinnati award-winning that takes spirit and innovation to the next level. And also Powerhouse was established to provide a suitable and convenient electricity from renewable primary energy supply, mainly focusing on wind turbines. So by having the innovation hub as the worldwide demand for electricity increase, we offer an innovative, efficient for the future wind turbine generation. So here is the main outline for our presentation, talking about the problem and solution and moving to the market and key customers, and then we will end with exit strategy. Okay, so what is the problem exactly? As we see here from the two videos, so the main problem is so the main problem is the low efficiency of the wind farms due to the wind turbines wakes, as we see. So what is wind farm? Wind farm is an electric generator farm that consists of multiple rows of wind turbines, as you can see in the video. So there are multiple rows of similar wind farms, and the second row are beyond, which operate in the wake with low wind speed, and that reduce the power. And the second video here, as we see, that shows the same how the wind turbines operate in very strong wake behind the first row. And also in the figure, there is a wind turbine are spaced 10 times the diameter of the wind blades, and that reduces the density of the wind turbine farm for a specific farm area. Okay, so what is the solution? Our solution is a new design that eliminates the wake behind the wind turbines and discharge it vertically up or down, according to the figure on the left. So also we see that on the right figure, there are a typical 3 rows from farm where the turbines are now can be placed in very short distance from each other because there is no wake behind them. Consequently, the distance between rows can be less than 1 turbine diameter, and also it will lead to improve the farm efficiency, and our design will enhance the speed of the wind for higher turbine efficiency, whereas the power is proportional to the velocity Q. Okay, so what is our advantage? Our solution increases the wind speed and power through a unique compression process. So we can operate in low wind speed, and because any wind speed below 2 meters per second will not be suitable for generating electricity efficiently. Because of the vertical exhaust, we can exploit the distance between the wind turbines where there are no longer wakes behind the turbines. So it's available to put some turbines close to each other without any effect from the front turbines, consequently no drop in efficiency and power. So making use of vertical exhaust to create levitation for wind turbine weight, which has advantage, especially offshore wind turbines applications. So where the exhaust can be used to reduce the stress on the wind turbine steering, which has big advantage in offshore in the water. So additionally, our design has more advantage, which reduce the cost structure maintained through reducing the fatigue, as there is no longer wake behind the turbines. And finally, also because the wake now is vertically dissipated and normal to the direction of the wind, so it has low noise. So we are targeting just the US market that has the 3 main areas: industrial, residential, and commercial, as shown in the table. And as we see that in the following chart, the North American wind power market share is consists of 3 main applications, which is commercial, residential, and industrial. Basically, we will focus on the residential and commercial market. Moreover, by 2027, as we see, the total market value will be around 42 billion. Also, the compound annual growth rate will be around 11%, which is a great indicator about the high rate in the market. And regarding the financing needs, so and of course, our startup will need fund to design and build and test our prototype and document the performance. We already have a homemade prototype, but we also already raised $5K from the UC Innovation Hub, and also we got accepted in Iowa I-Corp. So we expect $1,000, and we will keep searching for funds. That's why we are here. And regarding the risk and mitigation, so of course there is a risk and related to barriers to the entry market and high cost of the startup and manufacturing. So we think we have a good chance for success because we have an innovative idea, technology, and cost-effective device with efficient system. And our key customers, as we mentioned before, is residential and commercial farmers that shape a good market in the US, like urban and rural areas. And regarding our milestone, so our team is planning to interview over 50 companies in the renewable energy system and raise fund and support the development to test and build the prototype, then document the performance and support the interview. So we can form a startup entity and register in the state of Ohio as a company, which requires funds. And regarding our exit strategy, so basically our exit strategy is to release our innovation of validation after proving our concept and design, because we are not expert in manufacturing and solution, as we are focusing on like we are like an institution related to science and so on. So we don't have enough experience in manufacturing and solution. So that's it. Thank you.
Oh, perfect. You're just exactly 7 minutes. That was great.
Yeah. So yeah, we are ready for your questions. Me
great.
and Professor Abdullah is with me.
Great. Your Q&A can begin.
Okay.
In your modeling, what are the cut-in and cut-out speeds assumed with this type of newer design?
The minimum speed is 2 meters per second to produce efficient electricity, but our system can double that or triple that because we have a unique compression process that will enable us to operate in very low wind energy. The maximum speed is, of course, is a storm. We can actually shut off the system using aerodynamic brakes.
That was actually going to be my next question to ask about weatherization of this equipment, given that there's just so many storms operating around.
Yes.
Curtailing wind generation in so many markets right now.
Yes, this is actually a very big problem. I'm using currently the state of the art is to use friction brakes or sometimes feather the plates of the wind turbine to reduce the loading on the plates. However, there are so many accidents in spite of that. And so fire accidents and usually require evacuation of a 5-mile area. So we have an aerodynamic, we can shut off the turbine by shutting off the compression process, and that reduces the wind speed way below 2 meters per second.
If I can ask, is it your vision that this technology will replace all horizontally designs, or do you feel it's more complementary, or is it able to access wind energy in places with less natural wind resources?
This is a great question. Actually, we think we are the next generation of generating electricity safely and economically, and increasing farms' efficiency and cost, reduce the cost. We are unique in the sense we are the only, we have no competitors in discharging the wake of wind turbines vertically up. They all existing wind turbines discharge in the same direction of the wind and require huge distances between the rows to gain the kinetic energy for next rows. So we will be able to place wind turbines within a 1 diameter distance, and you can see that that will improve the density of the farm, power density of the farm. So we think we are the future.
Thank you very much. That's the end of your Q&A. We will have 1 minute
Thank you.
Thank you very much. And the next team can get ready. It's a Beta vertical access wind turbine.
Can you see the screen up?
We can, it is not yet in presentation mode. If you could make it in presentation mode, please.
What about now?
We can't see it right now. So if we can't do it in presenter mode, that's fine. Well, you will just be able to see your screens on the side. We are going to download your backup presentation because we're not able to see it right now when you share it. Is it possible that you have two screens open? Sean, are you there? Sean Lynch? Sure.
Would it be possible for us to go after the next group?
Yes, we will switch groups.
Okay.
The next group is going to be UD Flyers. If you can share your screen and your video, I will let you know when we are ready to begin. Okay, Team UD, you may begin.
All right. Good afternoon, everyone. So we are Team UD Flyers, and presenting today for our pitch, sodium-ion cathode research for sustainable battery development. Oh, there we go. Sorry about that. All right, there we go. My name is Scott Ridley, team captain, and my partner, Subhatha Ranjendran, is actually taking an exam right now, so she could be here at any minute. But in the meantime, you got me. We're actually both students here at University of Dayton with undergraduates in chemical engineering, and both currently pursuing Masters of Science degrees in renewable and clean energy. So while we both were born literally worlds apart, this program has actually allowed us to form a pretty close friendship, but also a collaboration. So the fruits of that collaboration are the projects that we're sharing today. So essentially the pitch is, we've actually developed a prototype sodium-ion battery that is safe, affordable, fast charging, and sustainable. And essentially we're seeking additional research funding to bring this technology to commercialization. So the advantages presented by sodium-ion batteries and our prototype in particular are safety, speed, security, sustainability, and affordability. Not an S, but close enough. With regards to safety, so this sodium-ion batteries and our prototype in particular is capable of operating at a much wider range of temperatures and is inherently, due to its chemistry, non-flammable. And again, because of the chemistry, It does not include heavy metals that might leach or otherwise cause ecotoxicity or human toxicity. They are capable of fast charging and also capable of discharging to 0%. So again, getting back to safety, this allows for safe transportation when discharged. So it also provides energy security. So the materials to make this are sodium, aluminum, abundant and domestically available materials that can be sourced anywhere in the world, releasing reliance on lithium specifically, and a lot of the challenges that come with that. These are very sustainable. So again, because of the materials, but also they are recyclable, energy efficient, and ultimately because of the materials and their ability to be sourced easily, they are up to 40% less expensive to produce than lithium batteries. And can be produced in any facility that's already producing lithium batteries. So the specific technology that we made use of are innovation in this space, because there are many people who are trying to develop sodium-ion batteries for commercialization. But our niche is within the cathode development using the sodium superionic conductor or NASICON method. So this provides high air and structure stability, high capacity and energy output. We chose this each of our competitors were each picking different technologies based on our performance standards. Ours, we're prioritizing safety, and performance, of course, but hey, Suba, come on in, we're going. So as I mentioned, our competitors, so this is kind of it's an exciting and emerging field. So there is no truly commercially viable sodium-ion battery on the market currently. That could change literally any day. So this is happening very quickly. CATL just announced that they're going to start manufacturing. So we are definitely in a race. So as you can see here, with our preliminary research on the prototype, the energy density that we were able to achieve is comparable to our competitors. You may note, though, that one of the downsides to sodium-ion in general is it doesn't necessarily have the same energy density as, say, lithium-ion. But the sustainability aspects, the safety aspects are absolutely worthwhile pursuing. Additionally, the applications that we're interested in, so again, with this market assessment, this is a great chance for things like small electronics appliances, but all the way up to things that don't necessarily aren't concerned so much with size or the scale of energy density. So things like grid battery energy storage systems. And ideally, the focus would be with regards to the grid energy for communities, either in developing nations or emerging economies who need safe and reliable energy storage. And this can provide that. So in terms of feasibility, as you can see here, with regards to grid storage, by 2025, it's projected to be sodium-ion batteries are projected to take up 75% of that market because they are well suited to those permanent stationary applications. And again, because of the less expense production costs, the opportunity is really great. Again, in terms of how to deploy this, any current manufacturer of batteries can easily switch to sodium-ion batteries. So this is really just a change of chemistry, not necessarily in the machining itself. So the impacts could be huge for commercial applications. So not only can sodium-ion batteries provide fast charging, safe transportation of batteries, recyclability, and affordability, the impacts, especially on emerging economies, means lives saved, environment saved, positive health impacts. So there's a ton that can be done here, and really this is helping. This would be contributing to the transition from a solely lithium-ion battery-based ecosystem to incorporating sodium-ion batteries and a more sustainable option. So in terms of a business plan, what we're really looking for is to secure our research, publish, patent, and then create that startup that we would need to then ultimately, potentially, for example, conduct a technology transfer at some point. So what we'd like to do though is start in the consumer electronics and devices market. So if you look at the bottom of that circle there, and make our way through to grid, and as we continue to optimize, as research continues, ultimately make our way to transportation as it may come to pass. And that's my time. So thank you very much. And I'm gonna switch really quick to laptop so that Suba can help answer some of the questions.
Hey, Scott.
Yes.
Thanks for walking us through the presentation. I have one question. Do you have a comparison between sodium ion, I mean, your product versus any lithium ion based battery product in terms of how much they weigh?
Yes, comparing sodium ion batteries and lithium weight.
It is like 50 times little bit higher, but we are working on the optimization of that. So with the thin film and the thin film cathode, it can be the similar lithium battery.
We're having a hard time hearing you.
Oh, sorry.
If there's any way you could.
I can clarify my question. The reason I asked this question is because if you want to have your product go into electric vehicles, then the weight of the battery unit becomes an important thing. So just wanted to see if you have an analysis in terms of how this compares with the lithium ion batteries in the current status.
Ideally, actually, we wanted to target with the small electronic devices and grid storage, just to have the feel of sodium battery in the market first. And then we are parallelly working on the optimization in terms of weight to be used for the EV industry as well.
Got it. Thank you.
Hi, I'm sorry if you addressed this earlier, but can you comment on the access to sodium versus other chemistries, and if there are environmental or ethical considerations to these different chemistries?
Actually, the competitive can be zinc air and aluminum air flow batteries, but many of them, like they are not electronically rechargeable. So this in terms of comparison of performance, sodium is in par with the lithium performance in terms of rechargeable nature and in terms of energy density compared to other one. Zinc air, lead acid, those are all like it has to be mechanically rechargeable.
And with regards to the potential impacts, so for example, our prototype uses predominantly a sodium electrolyte, aluminum, and then a hard carbon. So there are the different competitors have different minerals that they might use that might have challenges from a mining perspective. Our prototype is kind of the niche that we're trying to provide is using those abundant, more sustainable materials. Especially in comparison to say lithium, by using the materials that we've provided in the prototype, you can avoid most of the issues with things like labor and human rights issues with certain conflict mineral mining, and then of course the ecotoxicity. So you could bury our prototype. I mean, please don't, but you could bury it with very minimal impact on the environment or human health.
Thank you so much, Team UD Flyers. I want to remind the judges that when they submit the forms for this team, this was team number 6, UD Flyers. They just went in the 5th place. We're really sorry, Scott. I know you needed to go after 2, and as soon as you mentioned that your partner wasn't there, I was like, no, we didn't. But anyways, you guys did a great job, and I'm really glad that both of you made it to the presentation.
Awesome. Well, thank you so much.
Thanks.
And we'll have 1 minute as we a beta vertical access wind turbine. How are you guys doing?
We're trying a different laptop, so hopefully that's going to work.
Okay, go ahead and practice sharing your screen while we have our 1 minute for the judges to submit their forms. It works.
Yay.
Okay, I will let you know when to begin. We'll wait one more minute.
Okay.
While we're waiting another minute, I'll tell another joke. How do wind turbines feel about renewable energy? They're big fans.
Okay, CSU Ohio Vertical Access Wind Turbine, you may begin.
Okay, hi everyone. We are CSU. We are a team of engineers that are working on a senior design project. For our project, we developed the vertical axis wind turbine. Since this is a new design to market, this is never before seen technology because we're actually building it as part of our senior design project. So we're going to start by explaining the technology to you.
So we have built a full-size functioning prototype. There are 4 main parts to it. The stator, which directs the airflow, the rotors themselves, there are 2 on either side, cassettes that house the rotors and allow them to be taken in and out, and the current electrical system for the prototype. So this is the general equation for generating wind power. There's a bunch of variables, but the interesting one here and the key one is the wind velocity, which you can see is cubed. So if you can maximize wind velocity, you can maximize power generation.
The stator acts as an improvement to the vertical axis wind turbine. The stator acts as an airfoil, which serves to increase the velocity of the wind around the unit. It's self-seeking. It sits on a 360-degree rotating base, which allows the airfoil-shaped stator to point into the wind passively. Some ancillary benefits are an increased safety for birds because of the shrouded rotating system. It has a lower visual and auditory signature, and the rotating shroud controls the maximum speed of the rotor. It's also easy to maintain.
So you can see we've done some simulation both in ANSYS Fluent as well as inside simulation and outside simulation in the field.
Okay, our next steps are to optimize our design through research, experimentation, and simulations. We are optimizing our design through prototypes, modular design through computer modeling, and we investigate a shroud that potentially controls the wind speed and reduces our visual signature and environmental effects. We'll also optimize our power collection through utilizing vacant spaces for solar panels, and we'll integrate solar energy and wind energy to optimize our power collection.
So now that you guys have had a brief walkthrough of what the technology looks like, we're going to get into the business side of things. A little bit of background on the market that we intend to target is owners of electric vehicles. This turbine is designed for urban and suburban application. It's ideal to sit on top of rooftops of large skyscrapers or in the backyard of a small suburban backyard.
So our final design, we estimate will produce a little over 1 kilowatt, and we see that being able to charge a battery bank, like in a garage perhaps. And you can use that battery bank to charge your electric vehicle or maybe other battery powered devices such as a lawnmower or a leaf blower, something like that.
So where do we fit within this market of residential wind turbines? The ideal wind turbine works on large towers, which is a city application, or large flat terrain, such as an urban or a suburban or rural backyard. Conventional wind turbines need a lot of free space to have enough wind pass over the land to make the blade spin. The way our design is optimized, it doesn't require all of that acreage. We can function our turbine on as little as 1 acre, which services approximately 21 million homes in the US. You can see to the map on the right, this is a map of average wind speeds across the US. And since that Rocky Mountain middle section is the fastest wind speed, That's where we plan to start that wind turbine promotion to generate buzz on the efficiency of our design. There are currently wind turbines on the market. They're expensive, ranging from $1,000 to $2,000 for a base model, producing the same power output that we would expect with our design.
Current strengths are the high efficiency design provides a cost advantage to conventional wind turbines. It requires less wind to begin the rotation of the rotor, has a low visual and auditory signature, a small footprint, and is modular. Each component is easily serviceable, and the components are also stackable. Currently, the weaknesses are a low recognition in the market. Not all stages, we're not at the stage for mass production yet, and it's a more complex design.
Our turbine is very unique and very patentable. We have the opportunity to be pioneers in the urban and suburban turbine market. This could attract investors and maximize our funding opportunities. Will bolster faith of our design through vetted review processes and ensure due diligence from professionals in our field. And we intend to get underwritten approval.
So how are we going to get this turbine to market? How are we going to incentivize customers to buy this product? We're going to start by doing demonstrations that showcase the turbine's competitive qualities. Once you experience the design, you'll see that it speaks for itself. We just need to get the word out there to show that our design is highly effective. We also plan to research and partner with current existing government incentives for green power. There's currently a 20 to 30% tax credit just for the installation of a small turbine in the home, and we plan to piggyback off of other incentives that are similar. We also plan to use social media to promote the product and generate a market buzz so more people hear about the design. And then also we plan to partner with electric vehicle or rechargeable battery device manufacturers, such as Tesla, Chevy, and DeWalt, so they could partner our wind turbine with their electric charging vehicle to create a package deal that lowers the barrier to sustainable energy for the consumer.
So for future goals, you can see them here, but with sufficient funding, we expect that within 5 years, we'd be able to produce 20,000 units.
Thank you guys so much for your time. We're happy to answer any questions you may have.
So I'm curious if you're making the case to residential customers. I saw the comparable of wind turbines at 1,000 to 2,000, right? If you're looking at solar, you know, it's much higher than that if I wanted to get solar on my roof. Wondering what kind of price point you're thinking about and a general kind of pitch to the residential owner on why they would get this rather than solar.
So our design is much less expensive than solar power. The thing that determines the price would be that stage of the mass production aspect that we're not at yet. Our current prototype is a relatively inexpensive prototype for what it can produce. But as far as like the business case in the future, we plan the module components, we plan to get more on like a large production scale. So pricing would vary as like funding and that develops.
Okay, thanks.
What kind of wind speeds would we be talking about to generate, for example, I think the EV charge, say, I think it's at 40 to 60 hours. Are we talking the Hummer or are we talking the Nissan Leaf?
No, so we're expecting 1 kilowatt of production at an average type wind speed. And that would be charging, when the car's not there, charging the battery bank. And then the car would be able to charge after that. But yeah, for 40 to 60 hours, that would not be a Hummer type battery.
And then you mentioned also the complex design. Any idea on what kind of O&M to expect for, we'll say the service side of, once this is built in the field, what kind of cost might an owner have there?
Are you saying as far as like maintenance?
Correct. Any kind of consumables, any type of inspection, replacement, anything like that to properly maintain a functioning system?
The idea of maintenance was built into the design, and it actually is one of its strengths and advantages because the turbine functions low to the ground, so it's easily accessible. And then every single component in the turbine is removable. So it's very easy to remove the rotor, remove the cassettes, and service each part individually.
I'll go with one more. Height of installation. Obviously, some residential rooftops could only be maybe 1 story tall. Are you assuming it's roof-based or on the ground, even at 5-10 feet, or is there an optimal height that you've been looking to design for and market?
So we've been looking at basically whatever height you have, you could install this device. And then if it were installed on the ground, the modular idea is that you could put another unit on top and they would be able to independently rotate and the rotors would spin at different speeds. So you could have a higher wind profile that you're capturing.
Thank you very much. That ends the Q&A. Judges, please remember that this was team number 5 when you fill out the judging form. We will take a minute and have Lehigh University team get ready to share their presentation and their video.
Hi everyone, can you see my screen?
Yes, we can see your screen and we can hear you.
Okay, thank you. Hi everyone, my name is Imad Yagmo. I am a PhD student at Lehigh University. Today I'm gonna present my proposal idea for my team under title PCM infused pervious concrete as a cooler, greener, and stronger. My team members are Lee Dayan and Julio Bravo. Okay, here is short introduction and surveying about the consumption of electricity. According to the U.S. Energy Information Administration, EIA, the residential sector in the United States consumes electric energy about 235 billion kilowatts for cooling, as we can see here in the figure, which was equal about 16% of total residential sector electricity consumption and 6% of total United States. Okay, the electricity or the source of the electricity in the United States, the main sources is natural gas, coal, and nuclear, provide 80% of the electricity in the United States. However, the renewable energy provide only 20% of the electricity in the United States. So for that, emission of the carbon dioxide, CO2, by the U.S. electric power sector were 51 million metric ton, or about 32 of total United States CO2 emission. Okay, for that, we need to provide cooler system, renewable cooler system, and our product is PCM pervious concrete, as I mentioned in the title. So what is the pervious concrete? It's a special porous concrete type that is made of single size of coarse aggregate with a small amount or no fine aggregate. The main characteristic of the pervious concrete, as we can see, is permeable concrete, allows to air and water to flow through it. Drainage, environmental sustainability, and the durability. Okay, what about the PCM? The PCM is phase change material. It provides more energy in less volume. Please take a look for this figure. This figure shows 1 kilojoule thermal energy stored in different material. For in case to store 1 kilojoule in water, we need 24 centimeter cube. In steel, we need 25.4, etc. Since the water, steel, rock, and concrete store the thermal energy in sensible heat form. However, take a look for the PCM case. To store 1 kilojoule of energy, of thermal energy, we need only 3.1 centimeter cube of PCM. since the PCM stores the energy in two forms, latent heat and sensible heat. The latent heat is absorb or reject energy when the PCM changes phase, as we can see here at the melting temperature from solid to liquid or vice versa, respectively. Phase change material PCM have been used since it has a high latent heat of a transition, high energy density, and low cost. Okay, what's our application? The main application for using PCM pervious concrete to improving the cooling system, okay? So in this slide, I will show you three main applications of cooling using PCM pervious concrete. The first one is improving central cooling in the houses and offices. Okay, we know in the summer or in the hot day, the efficiency of the central AC goes down. So we need more energy, which means more money and more CO2 emissions. So we need to improve the central AC by adding or install the PCM pervious concrete in the duct, as we can see here. The hot air flows through the PCM pervious concrete. The phase change process, since the PCM pervious concrete is a porous media or permeable media, the phase change process works to absorb the heat and cool down the air. So we improve the AC central system and decrease the electricity consumption. Another application, or the second application, is the roadway and pavement. Okay, we know the contact between the vehicle tire and the pavement generate heat energy. Okay, the PCM pervious concrete, as we can see here, works to absorb this heat energy and cool down or cool the air on the traffic area. And this has helped in like the Gulf countries, where in the summer, the weather on the street, it's too hot. So we can cool down the weather, since the Gulf country, like in 2022, Qatar had a host for the World Cup, and in 2030, maybe Saudi Arabia will be the host of the World Cup. So we can use the PCM pervious concrete on the street of the hot countries or on some states on the United States. The third application is a green roof. Its work to regulate the temperature, provide isolation for building below. Okay, marketing assessment. Now here we can see the difference between the pervious concrete and the PCM pervious concrete. The availability of the pervious concrete is available on the market. However, the PCM pervious concrete is not available. It's a new idea. Okay, the thermal storage type. The pervious concrete can store the thermal energy as a sensible heat only. However, for the PCM pervious concrete, we can store the energy in sensible and latent heat form. The cost is not expensive, since it's a concrete fabrication, it's too easy. Okay. The potential impact for the building owner and developer provides sustainable energy efficient option for indoor, like AC system, and outdoor application. Help building owner and developer to meet their sustainability goal and reduce environmental impact. For the contractor and builder, offering diversity option on the material. For the energy transition, improving central cooling system, the energy demand will be decreased. As I mentioned, the efficiency of cooling system will be increased. This type of concrete can help to reduce the greenhouse gas emission, conserve energy, mitigate the impact of the climate change. Okay, the business plan. For the marketing and sales side, we want to focus on digital and traditional marketing methods, such as engine optimization and social media. And we want to develop relation with the architect and builder to promote benefits of PCM pervious concrete. Sales will be responsible to developing lead nurturing relationship with the potential customer and the closing deal. For the operations, we want to manufacture the responsibility with the manufacture and distribution of the PCM pervious concrete, develop relation with the concrete maker and supplier to ensure steady supply of material. The COO will be responsible for managing our production, logistic and supply chain. For the financial plan, projection.
Iman,
Yes.
We are done with your 7 minutes,
Okay.
but if they have any questions, really, oh, you were so close.
Yeah.
You can leave it on your previous slide in case they want to read the rest, but we can begin the Q&A now.
Okay. Leave account.
Would you be able to go into the economics a bit just to understand what kind of materials this would be displacing and any incremental cost considerations, let's say for an architect or a developer?
What? Can you say again?
Sure. Would you be able to go into any of the economics around what a developer might expect to see here in terms of using this type of material instead of the status quo?
So yeah, I think we compare with the normal pervious concrete. We incorporate the PCM into the pervious concrete. That is the added value to the pervious concrete that can make the pervious. We add the diverse, so we can make the product distinguished from the normal pervious concrete on the market. Is that answering your question?
It did. So it's a part of the concrete rather than a direct substitute to it. It's an additional thing. Okay. Is that able to be, I'll say, locally or regionally sourced wherever this is going to be used for the PCM?
Yeah, there are many types of the PCM, and each PCM has the different melting temperature. So for the different cases, we will use the different PCM with different phase change temperature. So for example, if we are going to use our product in the cooling system, then we will find a melting. We will find a phase change material that has the melting temperature that lower than the hottest period of the day,
like 20 degree, 25. Is it answer for your question?
Yes, it did. Thank you.
Okay. Any question?
Okay, I think we're done with questions. We are going to take a 5-minute break. Thin materials, if you could just be ready. And I will announce when we are coming back. So please join us back at around 2:41. We will see you then. Team Fin Materials, if you could pull up your presentation, and I will still give the announcement when you're ready to begin, but let's just make sure your presentation is ready.
Sure.
We're gonna give everyone until 2:42, so one more minute to come back, and then I will cue your presentation. Okay, you may begin.
Hi, everyone. I'm Varun Shankar with Physics Inverted, or Fin Materials, and we are accelerating simulations for materials of the future. So climate change is, of course, one of the greatest threats our world is facing, and we need to substantially reduce our emissions to stay below this sort of 4-degree warming threshold to avoid a climate catastrophe. So our emissions come from a variety of economic sectors, which means we need widespread and, more importantly, rapid development of new green technologies to meet our climate goals. Now, materials innovations are going to be key to developing these technologies, especially when we consider the impact that sort of new materials or advanced manufacturing techniques would have on these industries. So, solar panels for electricity production, green methods to synthesize ammonia, or new battery materials for transportation. Unfortunately, the current materials paradigm is about a 30-year timeframe for development. And so we can see a few sort of examples from history of materials that have been developed, and we have this very consistent timeline from discovery to market penetration. The problem is that current materials design workflows are highly inefficient. So the vast majority of development time is spent in the lab in this iterative process of testing each candidate material until we find the one that matches our desired properties. And so while there is some initial screening of the design space, these typically don't sort of meaningfully reduce the number of candidate materials that we need to test. So our proposed methodology to kind of address some of these issues is to incorporate material simulations into the screening procedure. And so the analogy that we draw here is with sort of CAD and simulation and mechanical design, and in the sense that we want to sort of rapidly iterate on new designs using computational tools prior to actually going out and spending the money to manufacture and experimentally test the designs. Now, the hurdle to overcome with material simulations today is that they have these accuracy cost trade-offs that currently make simulation enhanced design impractical. So either we have sort of low cost, low accuracy simulations that can, again, sort of meaningfully reduce the design space, or we have high accuracy simulations that are in fact so costly that it would be more cost effective to actually just run an experiment. And so what our innovation does is kind of bend this accuracy cost trade-off such that we can access high accuracy, low cost simulations that actually make simulation enhanced design feasible. So we've identified a few competitors in kind of the software materials space. Companies like Citrine sort of focus on more of this initial screening using data-driven informatics approaches, and so they're kind of limited in the insights that they can give us. Other companies like Schrodinger, who do sort of do material simulations, are constrained by current simulation techniques. So our goal is to kind of reduce this 30-year development timeframe down to 10 years using our simulation enhanced workflow. And so the benefit of simulation is that it scales more favorably than experimentation with system complexity. And so we hope to kind of maintain this linear growth of materials development as we reach market readiness. Now, our core innovation comes from technology that we've developed over the last few years of our PhD. We have AI models to replace some of these costly simulations for rapid iteration of new designs. We have differentiable simulations, which allow for efficient optimization of materials properties. And all of this kind of leads to our high accuracy, low cost multi-scale simulations that can give us device scale insights at atomic scale accuracy. Now, our technology could feasibly be applied to a number of different material spaces. So potentially carbon membranes for carbon capture, photovoltaics for solar cells, or new materials for grid energy storage. We're first deciding to focus on the battery electric vehicle market, which is projected to be around 200 billion by 2028. And so our market strategy is to kind of develop these new materials using our technology and license that to materials or battery manufacturers for them to use in their own products. And so this gives them the benefit of kind of outsourcing a lot of that expensive and time-consuming R&D to us. And this gives us the benefit of sort of avoiding the high capital cost of building out a factory to manufacture these materials ourselves. So the first product that we intend to develop is an interface material to enhance solid state batteries. So these are going to be critical to actually enabling solid state batteries, considering the fact that right now solid state batteries, have a bunch of degradation problems that come from sort of dendrite growth, and so our interface material will kind of mitigate some of these issues. So this will enable sort of shorter charge times and additionally eliminate fire risk, which are both sort of key psychological barriers to more widespread consumer adoption of electric vehicles. So we've looked at sort of historical pricing of lithium-ion batteries. These prices have dropped pretty significantly over the last decade. They're expected to kind of plateau a little bit over the next decade. We've identified a few customers that we might target, sort of large materials battery manufacturers, CATL, Panasonic, Samsung, as well as sort of smaller battery companies, specifically that kind of focus on solid state batteries, as well as automotive OEMs. And so our plan is to kind of partner with at least one of these to manufacture our new electrolyte material at a price point of $1 per kilowatt hour. And so this corresponds to about 1 to 2% of current lithium-ion battery prices. So we've outlined sort of a roadmap here for our development timeline and some key aspects in the next 2 years. We aim to sort of refine our software stack for battery materials and cultivate those first customer relations. By the end of year 4, finalize that sort of first product and begin scaling up production with our commercial partner. And so we anticipate a total development cost of around 2.1 million, which means that we need a market penetration of around 2 gigawatt hours to achieve profitability. And so we think this is feasible considering that sort of a pilot battery line has a capacity of around 1 gigawatt hour. And so running that for 2 years would recoup those development costs. So if we're successful, our product will certainly have a positive impact towards a number of different stakeholders. The customers that we're interacting with will have faster R&D timelines. The end users sort of driving those solid state battery EVs will be safer in their cars. They'll be able to drive for longer. And then on sort of a more holistic level, our technology will be helping towards driving the transition towards green transportation, so reducing kind of CO2 and particulate emissions, which tend to disproportionately impact disadvantaged communities. And so our vision is really to sort of be a part of the solution when it comes to stopping or reversing the effects of climate change. So thank you again. We're Physics Converted Materials, and here's our team. Happy to take questions.
Do you anticipate going into other markets after looking at the lithium-ion batteries?
Yeah, absolutely. So the reason that we've sort of chosen batteries at first is because that's sort of where our domain expertise is. And so we kind of want to prove out this technology in this area first. But our technology can certainly be applied to a number of different areas. We're very sort of flexible in terms of other electrochemical processes. And so we could certainly expand into other segments like fuel cells or other sort of materials processes.
With the recent IRA announcements and obviously a lot of battery funding and research and manufacturing really coming to market here in the next couple of years, have they already maybe locked in designs and manufacturing, or is there a time and a place where you see this solution being implemented even after a site has been built out?
Sure, yeah. So we've done actually quite a bit of customer discovery from the NSF I-Corps program. And so we've talked to a number of different, battery engineers. And, basically what they've told us is there very much is a need for this. And regardless of how sort of mature their product is, there's always a need for sort of materials discovery and refining their existing products. So we don't necessarily think that sort of, things that are locked in may not, have a need for additional refinement. So yeah, and specifically for solid state batteries, these obviously are not sort of in production yet. And so we would certainly have an impact there as well.
Thank you.
Thank you very much. We will have 1 minute for the judges to complete their forms. The next team will be new H2. If you can please have your presentation ready. I will let you know when to begin.
While we give the judges another minute, I'll tell another joke. What's a solar panel's favorite exercise?
What is it?
Circuits.
New H2, you may begin.
Okay. Good afternoon, everyone. My name is Tejaswini, and I'm joined by my teammate Keith, and we are Team New H2 from Case Western Reserve University, and we will be talking about our software that is set to revolutionize emission-free hydrogen production. So as global energy demand continues to skyrocket and several regions face an energy crisis, hydrogen, the most energy-dense fuel source known to humanity, could be the answer. The most common method for hydrogen production today is steam reforming of methane, which releases an abundant amount of carbon dioxide. But what if hydrogen production were to be emissions-free? This is where pink hydrogen enters the picture. Integrating electrolyzers with nuclear power plants to utilize their thermal and electrical energy results in a carbon neutral production process. As of today, companies like Exelon, Bloom Energy, and Westinghouse are partnering with nuclear power plants to test their electrolyzers. However, because of the high cost associated with current integrations, we are yet to fulfill DOE's mission of bringing down hydrogen costs to $1 per kilogram. And this is what the hydrogen prices look like based on the source. And you will notice that the more sustainable options tend to be more expensive. So now we're going to talk about how our product can help lower these hydrogen production costs. So we plan to make use of the fluctuating energy demand that results in a dynamic pricing system, also known as time of use rates. The plot that you see is from PJM interconnections, and you can see throughout the day, the energy demand continues to fluctuate. So after analyzing the changing energy demand throughout the day, we can use nuclear energy to power electrolyzers during off-peak hours instead of selling all the energy to the grid. I'll pass it on to Keith to explain our software.
Yeah, so just getting into the details of our product, the new H2 software package is aiming to reduce the price of pink hydrogen by taking advantage of inherent inefficiency that's associated with nuclear power. So since nuclear power is always generating the same amount of energy all day long, and the amount of energy demanded by the market fluctuates throughout the day, by hour, and also throughout the year with the seasons. Our software package is going to take in that demand data from sources like PJM, as well as live hydrogen fuel prices and fossil fuel prices in order to determine the optimal power distribution for a nuclear plant between selling their power to the grid and using it to power an electrolyzer that's going to generate hydrogen. And basically the goal of the software is to allow the plant to operate at the most profitable state at any point in time. Next, yeah. Getting into some features that we kept in mind while designing the software. First and foremost, our primary goal is to have the software be responsive to market inputs, essentially making sure that we're always using the highest quality, most recent data for our inputs, so that it can account for rapidly changing market conditions. Secondly, we want this to be compatible with existing power plants. We want this to be something that's easy to integrate, so that it's an additional incentive for nuclear plants that are looking to get into hydrogen production. And thirdly, we want this to be profitable. We want to enable these plants to reduce their operation costs, and we want to diversify the revenue stream by opening up hydrogen as an additional option. So getting into motivation for these plants. So So far in the United States, 4 plants have begun the process of integrating hydrogen production into their plant. So we're looking to try and further incentivize this process. So first and foremost, the hydrogen that they produce can be used to replace petroleum-powered processes on their plant. So that sort of mitigates the risk associated with the current challenges in storing hydrogen. There wouldn't be need for long-term storage if operations on plant could be replaced by hydrogen instead. Secondly, the hydrogen could be sold and stored and essentially just trucking it away and selling it. And thirdly, again, since nuclear is a constant source of energy and energy demand is always fluctuating, the software offers the opportunity for these plants to increase their revenue and become energy independent. So getting into our business plan, the hydrogen market is currently limited, but by the end of this decade, we're looking at potential expansion into residential and transportation sectors. So again, like I mentioned, there are these 4 plants that have already begun to integrate hydrogen production. And our business is focusing on encouraging the other 88 nuclear plants in the United States on incentivizing them to try and do something similar, and ideally with the use of our software to optimize their output. Again, our largest competition, like we saw on the slide with the prices, is the steam methane reforming industry, which accounts for 95% of total hydrogen production today. However, the amount of power that's generated by the nuclear power plants in the United States offers the potential to match and exceed that amount of hydrogen production if they're repurposed to produce hydrogen. Obviously, the large barrier to entry there is the upfront cost for the integration and electrolyzer. But one thing to keep in mind with the Inflation Reduction Act, there's actually a pretty large incentive for this. And there's pretty big tax credits that will drive down the price per kilogram of pink hydrogen. So just another potential advantage. And here's just a look at our timeline. Getting through this month, we've just about wrapped up our proof of concept for the software. In March, we're going to be attending ARPA-E and looking at pitching the software. And then in April, we're going to be looking towards patenting the IP and ensuring that our software is compliant with cybersecurity regulations. Obviously, in the nuclear sector, there's a ton of regulations. And our team is not totally equipped to ensure that our software is meeting that. So that's something that we're going to be looking into pitching and receiving additional funding to try and achieve that by April. And then May, we're just going to be meeting with people in industry and getting feedback to try and improve our product.
Thank you so much. That's your time. We will now switch to Q&A.
Are you anticipating that the nuclear power plant owners would also own the electrolyzers, or would that be a separate company that owns the electrolyzers?
So I think currently with our business plan, the plan is to partner with electrolyzer companies, so companies like Bloom Energy or Exelon, and sort of also give these companies an incentive to like partner with us, because that makes their device, like the use of their device, more feasible. So yeah, to answer your question, the electrolyzers would not be owned by the nuclear power plants, but instead by other companies who manufacture.
I have a question regards to your one of the previous slides, I think, where you mentioned time of use rates.
Yeah, I can try going back to that.
Could you just give us an idea in terms of how quickly can this technology be ramped up? Or I'm looking at it from the point of view of dispatching. Like if you want to continuously capture like the high prices that, you know, with peaking demand that come during different times of the day, how quickly can this technology like ramp up and be able to dispatch power?
That's a really good question. The ramp up and ramp down times depend on the kind of electrolyzer which is used. So alkaline electrolyzers, which I would say are the most mature electrolyzer technology, have ramp times which are on the scale of seconds. So with that, it is pretty quick. However, we are seeing newer solid state electrolyzers which reach a really high temperature. So with electrolyzers like that, you get higher efficiency in terms of hydrogen production, but the ramp times are in the scale of minutes. So it's again going to depend on the kind of hydrogen production that each power plant is looking to have.
Really informative. Thank you.
A question on maybe other uses that any additional capacity could be used for. Is that seen as part of your competition, say Bitcoin mining?
So that is something that did come up when we were like trying to gather more feedback. So I think right now we are trying to focus on the nuclear energy market, but if our proof of concept is successful and we get positive feedback, it could potentially be used for other applications, as you mentioned, for Bitcoin mining.
Sorry, same question, maybe repurpose it a little bit. If you have additional capacity available at a nuclear power plant, I understand it would be used through the electrolyzer to create hydrogen. Are there other applications though that would compete against saying that hydrogen is the most economic benefit as opposed to some other end use product?
Yeah,
Go on, Keith.
Yeah, I was just gonna take that one. Yeah, like we've had a similar feedback asking about like a battery bank or yeah, like you mentioned, Bitcoin. I guess, however, the way the software is developed, it could very easily be adapted to meet either of those markets. Our focus on hydrogen comes from, just a perspective that we have a strong belief in that industry's growth over the next decade. So we think there's a huge potential there. But yeah, it could definitely be repurposed for other uses like that.
Thank you very much. That ends the Q&A. The next team is the critical smelters. If you could pull up your PowerPoint, we will have 1 minute for the judges to complete their form now, and then I will let you know when to begin.
All right, we have another joke for you. Why do fluorescent lights hum? Why? Because they forgot the words.
Okay, critical smelters, please begin.
Good afternoon. My name is Ben Holcomb. I'm joined by my co-lab mate, Yuan Ma. We're both PhD students here at Case Western Reserve University in the Chemical and Biomolecular Engineering Department. And today we're going to report to you our novel process for a sustainable, efficient, and low-cost method of extracting critical materials. So a little bit about critical materials and more in particular rare earth elements. So critical materials, for those of you who don't know, are materials which are demand is very important. For example, lithium is one that we talk about a lot, but rare earth elements tend to fall into that category as well because they're scarce. Our lab tends to focus on neodymium, and the importance of neodymium is that it goes in neodymium iron boron permanent magnets, which are in your cell phones, your computers, missiles, electric vehicle motors, wind turbines, they're everywhere. To bring it down to earth a little bit, a Tesla Model S has roughly 5 kilograms of neodymium iron boron permanent magnets in them, and you see Teslas everywhere. This is important because the United States primarily imports rare earth elements. You can see this graph on the circle graph here. We participate a bit in the mining, but really the separation, the refining, and the magnet manufacturing, we don't have a significant global contribution to. So we really need a sustainable and domestic method of producing rare earth elements, and in particular neodymium. So we kind of have the status quo here on the left-hand side of how it's made. It's an electrolytic process. So you have two electrodes, an anode and a cathode, and at the cathode, you're plating neodymium metal, which is brought to its liquid form because it's at very high temperatures. But at the anode, you actually consume the anode, which is carbonaceous in nature. You're generating carbon monoxide, carbon dioxide, perfluorocarbons. This is a very difficult to control process. It is energy inefficient and can only be performed in a batch operation, and that results in a lot of heating and cooling associated costs. And the process that we are proposing and that we are already successfully implementing on a lab scale is a process that produces chlorine gas at the anode, which is something that we recycle upstream to make our feedstock. And it is done at a lower temperature in a batch process, although there is potential for a continuous process, which would remove all the associated heating and cooling costs. So to kind of understand the market of neodymium, like I mentioned before, the need for neodymium iron boron permanent magnets is only increasing. And you can see from this DOE projection on the right-hand side that our domestic need for neodymium is already in the tens of tons per year. And you can extend this to a global level where it's about an order of magnitude greater across the globe. So this need is not going anywhere anytime soon. And if we produce our neodymium utilizing greenhouse gas producing methods, we are going to continue to be in a lot of trouble in terms of our CO2 contributions. And like I mentioned before, we only do the mining. We don't do the separations, the refining, the manufacturing, and we badly need a self-contained supply chain here in the United States. And with that, I'll hand it off to my colleague.
So let me talk about the economic feasibility side of this process. First, the price of neodymium ranges from $60 to $250 per kilogram. So the major cost of this process is the feedstock and the electricity. Say we have the neodymium oxide is lower than $10 per kilogram, and hydrochloric acid is around $0.2 per kilogram, which these chemicals can be generated in a closed loop process, can be recycled. And then the electricity is $0.1 per kilowatt hour, and for 10 kilowatts hours of electricity, we produce 1 kilogram of neodymium. That means we just use $1 of electricity to produce 1 kilogram of neodymium. And this process gross margin will be larger than $50 per kilogram. So the impact of this work is that this is a major step towards the domestic decarbonization of the transportation, electricity generation too. So say for electric vehicles manufacturing and renewable energies development. And the second impact is that it lucrated the manufacturing careers located in Cleveland, Ohio. So Cleveland used to be a manufacturing hub, but now it's largely disappeared. So this impacts the competent workforce to be underserved. And this process has the potential to bring in the manufacturing back to Cleveland and serve this community here, and also give the equal opportunities of employment to the city. The third impact is that it increased the technology accessibility to phones, laptops, electric cars, because the whole process gives a low cost of neodymium. So it actually lowers the cost of manufacturing these electric devices. So our plan is that we want to have the SBIR grants for small to medium commercial scale production. So far, we have the LLC already in place and multiple patents has been filed. In the lab, we can have highly pure neodymium metal produced by using low energy. And the second plan we have is we want to partner with industry for larger scale production. So far, this project is actively coordinating with major players in the chemical and mineral industries.
Thank Thank you very much, and we look forward to all of your questions.
Thank you.
I'll come up with one. Materials engineering is obviously a complex and ever-changing science. Can you give kind of a little bit of a history of how long neodymium has been used and what the forecast is expected to look like with the, for example, EV growth? Is it the material of choice and default, or is it on the fringe? Kind of where are we going?
Yeah, so at present moment, I mean, there are labs dedicated at, for example, Ames National Lab to trying to make substitute magnets, and also to try and make some of these intermediate magnets that are currently being filled by sintered neodymium iron boron magnets. However, the time to commercialization, I think, is probably a decade or two out at best, and there's no real good forecast for seeing a downswing in the need for either bonded or sintered neodymium iron boron magnets, at least at present.
I'm glad to hear there's no downside. I notice, of course, this is an aggressive decarbonization scenario.
Yep.
What does it look like under, I'll say, status quo?
Yeah, I mean, so that 2020 demand is just like a pulled figure. That's not actually a projection. So this was pulled from a 2022 DOE deep dive assessment. So that is just, what was purchased outright. I think that really depends on how quickly the EV market can take off, how much people are implementing wind turbines, things like that. But certainly the data storage side of it, I mean, laptops, phones, that sort of demand is not going anywhere and is probably only increasing as accessibility increases. So.
This question might be a little bit broad, but do you know if your plans might fit within the Inflation Reduction Act? Oh, sorry, I can't see. Have you had a chance to look into how the IRA looks at multipliers and incentives for technologies like yours?
That's not an avenue we've explored yet, no.
I'll just say
that
there's a lot of enthusiasm and motion in the private sector, so this seems to align quite strongly.
Mm-hmm. Yeah. The industrial interest so far has been very strong, and I wish I could name drop, but since NDAs are in place, I will not do that. So.
Yeah, I anticipate a lot of it is about domestic manufacturing, domestic sourcing of goods. Yeah.
Yeah.
Great. Thank you very much. That ends our Q&A. We will now take 1 minute for the judges to complete their forms. When we return, we will have eDream Home. So if you can please start sharing your screen, we will wait 1 minute and I'll let you know when you can begin.
Okay, another joke. Why can't you trust an atom?
Why not?
They make up everything.
eDream Home, are you able to share your screen?
Okay, while we're getting set up, I'll tell y'all another joke. So Hagrid goes to Harry Potter, says, "You're a unit of power, Harry." And Harry says, "I'm a what?"
Okay, well, we're trying to get a hold of Team eDream Home. We are going to skip ahead and go to direct recycling of battery manufacturing waste. Spencer, are you able to share your screen?
Yep.
Okay, once your presentation is up.
I'm ready whenever you are.
Okay, are you able to go into present it? Oh, great.
Can everybody see my screen?
Yep, you
Okay.
can begin.
Sarah, I just want to start by saying thank you so much for the jokes. We've been really appreciating them over here. So keep them coming because we love them. But yes, I am Dominic Frazone. I am a PhD student at the University of Akron. I've been working on this energy project for the past 2.5 years now, and I am so lucky to have joining me Spencer Fraze and John DePaulo, who are 2 undergraduate students working on a senior design project. And of course, we have Sai as well, who is here for legal advice and moral support. So basically, the fundamental goal of the project is to apply a hardware as a service business model to a traditionally heavily industrialized commodity market, which is battery recycling. So without further ado, Spencer, if you'd be so kind.
Thank you, Dominic. The world as we know it is changing at a rapid rate. Currently, battery manufacturing are being incentivized to produce more volume, allowing the US to be less reliant on fossil fuels. EVs and batteries will play a huge role in the transition to green energy. To support this growth, several battery manufacturers will open battery plants from now through 2030. In the next 6 years, the manufacturing capacity for batteries is supposed to increase by 10 times, with 13 battery plants expected to be completed by 2025. This picture shows the current and future locations of battery manufacturing plants across the country. To continue to support this growth, efforts are being made to recycle scrap to be reused in the manufacturing process. Manufacturing scrap will be the primary source of recyclable material for the next decade. The current flow of recycling a battery is as follows. Waste from a plant gets shipped to a place in the US where it will be chopped to tiny pieces. Then shipped to Europe, where the waste will be recycled using toxic, hydrometallurgy, and pyrometallurgy techniques, which I'll get into more later. From there, it will be sent to China, where the raw material will be refined. Then it will be sent back to Europe, where it will be determined where the material will be sent. Then finally, it will go back to the battery manufacturer to be used in a battery. This logistically convoluted process produces an unacceptable amount of greenhouse gases during its 17,000-mile journey around the globe. On top of this, hydrometallurgy and pyrometallurgy recycling techniques use acids and toxic solvents that are extremely hazardous for the environment. During this recycling process, the material that was perfectly refined and ready to be used in manufacturing is now broken down into its raw form again. The current recycling process increases our foreign dependency due to the fact there are no refining plants in the US. This creates supply chain insecurity. Along with the issues above, there is a general resource scarcity in the world that includes precious materials used in batteries that will be the limiting factor to the EV market. While these new plants are going to help support the growing EV market, they are incredibly inefficient at the start of production. In the first year, a battery manufacturer may only yield approximately 37% of its max capacity. Year 2, 75%, and year 3, 80%. With this comes a lot of waste due to low yield of batteries.
Our solution to all these problems is a machine that is low cost, compact, and environmentally friendly. This patent-pending machine can accept waste directly from the plant, which is then upcycled using an environmentally friendly solvent. This means that the manufacturer will recycle their material will receive their material in its original state. With this direct recycling technology, all the current recycling inefficiencies can be addressed and eliminated. This direct recycling process allows battery manufacturers to save more money and have more control over their supply chain. To implement our technology into battery manufacturing plants, there's a 3-step plan that we proposed. First, acquiring agreements from partners to obtain the proper amount of waste needed to test our machine. The main target partners are battery manufacturing companies such as Rivian, GM, and iMany. Our team has already established a collaborative relationship with GM, who is a big player in the battery manufacturing industry in the United States. The second step is tech implementation. Currently, a prototype is being built that will allow us to test the construction of the machine and adjust where necessary. After technology demonstrations, we will move forward with installing machines in the manufacturer's facilities. The third and final step to our plan is customer agreements. Our initial customer discovery confirms that battery manufacturers are interested in our patented machine to help them reduce battery manufacturing costs and supplement current production capacity. With this initial interest and our hardware as a service business model, the group will look to continue growing our relationships with manufacturers. The hardware as a service business model allows the battery manufacturer to retain their material at no upfront cost. Yes, I said that correctly, no upfront cost. Currently, battery manufacturers buy new active material for about $30 to $40 per kilogram. Recycling companies currently pay manufacturers $12 per kilogram to recycle their waste. On a prototype scale, the cost of processing the material through our machine is $7 per kilogram. This allows us to make a profit of up to $21 per kilogram of waste. Now you're probably asking yourself, how much waste do manufacturing plants create in a year? The numbers are incredible. In the US, there will be approximately 39,000 tons of waste in 2023, 72,000 tons in 2024, and 136,000 tons in 2025. From the numbers above, the total addressable market would be around $819 million in 2023, $1.5 billion in 2024, and $2.9 billion in 2025. It is essential for direct recycling to capture this market to not only prevent the continued use of the currently environmentally hazardous recycling methods, but also help with the transition to green energy in the United States. With battery manufacturing increasing at a rapid rate, the United States is at a crucial crossroad. Our application of direct recycling will reduce the environmental harm caused by established recycling methods, reduce the mining of cobalt, which is associated with poor working conditions and child labor, and support the new EV transition by helping manufacturer economics and incentivizing accelerated growth. As manufacturing plants across the United States implement our machine, this will support new job opportunities for those who may have experienced job loss due to the energy transition. Thank you for the opportunity to present in front of you all today. Now we're open to any questions that you may have for us.
Can you talk a little bit more about the technology?
Yeah, absolutely. So direct recycling is kind of a really broad umbrella. Our specific application of it uses an environmentally friendly solvent to remove the active material from the aluminum foil current collectors in a way that doesn't damage the particle morphology or composition. Yeah, as you may have noticed, we didn't really talk too much about it. We really tried to focus on the business model here.
What kind of recovery ratios are you looking at if you have, let's say 1 kilogram going in of a given material? What do you get out on the back end? And how many different materials are we really talking about here? Is it 2, 5, 20?
Yeah, this is a great question. So for that $7 per kilogram cost of operating the machine that we listed, that's about a 75% efficiency. Currently at a prototype scale, we're at about 85%. How that varies is going to be manufacturer dependent. So the whole concept is that we can build a machine that is specific to an individual manufacturer, sits within their facilities. So we can change individual parameters about the shredding speed, the mesh size, or the composition of the solvent is really the secret sauce to increase that efficiency for a specific manufacturer.
The costs that you were able to quote roughly, yes. Are you able to break those down a little bit? What are the components to the dollars per to recycle?
Yeah, so for the $7 of cost, that's broken down into the amortization of the hardware, the recycling cost for the solvent that we use. It's fully recyclable, so we're able to extract the PVDF that we had used back out. And potentially that could be in another market where that PVDF has residual value and we could sell that, which is not included in the profit figure that we list. But those are basically the two main costs, is the amortization of the hardware and the recycling cost for the solvent. So now, Tim, you have also mentioned, asked a couple of other groups about the IRA. We view this as being fundamental to a battery manufacturer's ability to achieve those percentages for domestically sourced material. This is a massive leap forward. Their recycling rates, the scrap rates are about 20%, which could really be the thing that puts them over the benchmarks that they need to meet to get that $30 per kilowatt hour manufacturing credit.
Yeah, I'll just say for some of our operations, to be able to do this on site could be a game changer.
Right. All of the regulations around transporting this material are circumvented entirely.
Thank you.
Yeah, thank you.
Have you tested this at volume? For example, GM is not a small company, anticipating a pretty high volume there potentially.
Yes, absolutely. We're currently at 1 kilogram. We are developing a prototype that's capable of processing 100 kilos a day. But as you know, the deep relationship with partners, it'll be a long, arduous process demonstrating to them that we can replicate their exact active material at a relevant scale. So for the GM plant, actually right in our backyard in Warren, Ohio, they produce about 2,000 kilos of scrap a day. Getting to that rate will require work. We project it'll take about 12 to 18 months.
Thank you very much.
Yes, thank you.
We'll have 1 minute for the judges to submit their scores. Is Zhang Wang able to share her screen from the eDream Home team? We'll give them 1 minute to hopefully be able to share their screen.
All right. In the meantime, I've got another joke for you. What do you call London without electricity? What? Lund off.
We so far have not been able to reach eDream Home, though they are on the call. eDream Home, is there anyone from that team in either the panelists or attendees? If there's an attendee that is not able to share their screen, they can send us a message through the Q&A. We'll give them another 30 seconds and then we will move on. Okay, we are done with presentations for today. Thank you so much to all of the competitors. This was an awesome array of energy technologies that you've shared business plans for. Judges, if you are able to finish your forms, can you please leave this Zoom, just the judges, and go to the deliberation Zoom? Hannah, you can also go there as well. In the meantime, we would like to ask all of the participants to fill out a impact questionnaire that was just shared with you in the chat. This is a questionnaire from the Office of Technology Transfer, sorry. Just to get more feedback on the Energy Tech Up competition in general so that they can improve it for next year. This is the second year and you guys were really, really great competitors. While we are deliberating with the judges, Daniel Tachik is going to be giving a presentation about another competition that the Office of Technology Transfer is hosting. We hope you enjoy that presentation, and I will let you know when the judges have come to their decision.
Okay, hello everyone. So while all the judges deliberate all of their presentations that they just saw, I just want to take 15, 20 minutes, however long it takes for them to deliberate, to introduce you all to a new DOE prize out of its American-made series of prizes, the Equitable and Affordable Solutions to Electrification, or EASE, pronounced EASY Prize. I'm personally very excited about this prize. Selfishly, because I would very much like to electrify more of my home. We added some heat pumps over the past couple of years, and it was certainly not easy to do that. My house is over 100 years old and gets very cold during the winter. So this exact competition is aimed at coming up with solutions, not just for homes like mine, but homes in all types of scenarios. So whether you own a home or rent, there are challenges with multi-unit buildings to be addressed as well that we'll get into. This prize could ultimately impact everyone participating in Energy Tech Up today, as well as those that are in the viewing audience today. So just a quick view on what to expect over the next 15 or so minutes. I'm going to give you an overview of the prize, some example technologies and illustrative scenarios. And then phase one is really what I'm going to be talking about, because that's kind of the nearest deadline in this prize. How to apply and what to submit, and then how to get support for your submission. So equitable and affordable are really at the center of what the DOE wants to do with this prize. And at the end of the day, what this prize hopes to accomplish is to demonstrate easy pathways towards electrification for homeowners. So approaches that are faster, more affordable, and simpler for electricians and contractors. Here's a timeline of how the prize process goes for this particular prize. And I want to remind everyone, or not remind you, I should tell you, and I'm going to remind you several times over the next 10 minutes, that this timeline and virtually everything I'm going to discuss in this presentation can be found in the rules document on the HeroX website. So we're in phase one already. Applications have been submitted since December of last year. And phase one is relatively modest cash prize relative to phase two. So the DOE is simply looking for a concept here, and they're hoping it's not a huge lift for teams. But the cool thing about phase one is the phase one prize is that winning teams will get a $75,000 voucher to use with the American-made network or the DOE National Laboratories for technical assistance for the second phase, the demonstration phase. And you'll work with a power connector within American-made to figure out how to spend that voucher most effectively and identify the gaps to fill with that technical assistance to make sure that your demonstration is impactful and impressive as possible. So these are the scoring criteria used for both phase one and phase two. I'm not going to go through each one verbatim, but the point here is that the DOE isn't just looking for something off the shelf. They're really looking for something that's cutting edge and forward looking. But you can basically see the name of the prize, equitable and affordable, in these criteria, but it's not just those two things. The solution also has to be able to scale to a large number of homes. It needs to have speed, so faster to implement than current solutions, et cetera, et cetera. So the first phase, as I mentioned, is a concept paper. They're looking for up to 3,000 words discussion of the technologies you're proposing and the demonstration you anticipate and the team you establish to make that demonstration a success. And your team can evolve. The team you put together in the concept phase may look different by the time you're in the demonstration phase. So after you've used the voucher as a winner of phase one to receive some technical assistance, your team may evolve based on what you learn. Excuse me. And you don't have to have every single last detail in place in those 3,000 words or less for the demonstration, but you have to give the reviewers confidence that you will follow through on the activities you've outlined in the concept paper to demonstration of your ideas. So once you get to stage two, that's where there's a much more substantial cash award of $1 million for first place. No strings attached, and you can spend that however you'd like. You're really given a lot of flexibility in not only how you approach the problem, but how you use the money in the long run to scale up. So ultimately, the DOE wants whoever wins this prize to have their technologies deployed in real buildings, not just in pilot demonstrations. So again, there are extensive notes on eligibility in the official rules on the HeroX website on this, but the gist is the DOE anticipates a whole spectrum of different innovators to bring their expertise to bear, and people are encouraged to team up. So you might have a killer idea for an app or a piece of hardware, but you might not have the expertise required for the full home solution. So reach out to others who might fill those gaps. And again, just for the purposes of time, I'm not going to go through this in great detail, but the full detailed rules of eligibility are on the HeroX page, which I will link to later in this presentation. And this full presentation, and actually an even fuller presentation of what I'm giving to you right now, it's actually an hour long, which is kind of why I'm moving quickly. That is also, I believe, available on the HeroX website on this prize page. So if you see something on one of these slides that you're not able to jot down fast enough, or you have more questions about, don't worry, this is all online. And of course, here's the link to the official rules. Again, I will put this in the chat at the conclusion of this presentation. So home electrification is quite broad, and for that reason, the DOE has shared some example technologies and illustrative scenarios to help get your creative juices flowing. So there are a lot of words here, and I'm not going to read all of them, but examples include technologies that support the sharing of electric loads, dynamic control of the electric loads. So for example, appliance load controls that are similar to existing technologies for EVs today. And in the same line of thinking, rather than focusing on the electrical panel of the home, focusing at the appliance level. So smart appliances and equipment that can optimize power usage is another example. And there are other examples here, but just wanted to highlight a few of those. So these are so those previously that I just talked about are example technologies. And then as part of the concept paper and ultimately the demonstration, we need those solutions applied to some sort of scenario and setting that is realistic, that shows potential in the market for innovation that could reduce costs or make home electrification easier. In the prize rules document, the DOE has outlined 4 illustrative scenarios that teams could address. Teams could address one of these. They could address multiple of these. They could also address a different, like a hybrid, different scenario, not included in this example of scenarios. But what's really critical is that a prize submission and in the concept paper, it must be framed around some sort of actual housing scenario, because eventually the technology that you are proposing and writing about in the concept will be, you will be asked to demonstrate it on an actual housing scenario. So these scenarios that are highlighted are where electrification is currently not easy. So there's a lot of potential here for innovation to improve the process to make it faster and cheaper. And again, all of this is on the HeroX website, just providing you with some very quick high-level examples here. In this particular case that I'm showing here, a single section HUD code manufactured home, it runs mostly off propane. So they're looking for solutions that transfer some or all of those loads over to electricity. And there's a lot of challenges here, one being the space constraints, for example. You have a really compact roof that would be really hard to retrofit thermally to increase the insulation on the roof of that house, providing a novel challenge which could be relevant if you're trying to electrify. Another scenario, and this is kind of what I referred to in the beginning, the low-rise multifamily building. Some of the challenges here are that some of the centralized services as well as in-unit services. So you can imagine you've got centralized heating units and hot water heaters that would need to be electrified. But then you have gas and cooking ranges in each unit. And then you have shared gas vented clothes dryers, shared gas vented clothes dryers in the basement of this building, all of which make this a pretty unique scenario from the previous manufactured home scenario. And the last 2 scenarios I'll go over they're both single family homes, the first being in a mild climate. So a unique aspect of the mild climate scenario is that one might consider EV charging. And again, these scenarios are flexible. So say you want to use this scenario of a multi-unit building, but build in EV charging there. That's totally fine. But in this scenario, you have a lot of gas-powered cooking equipment. You have the 4-burner cooktop and separate double stack wall ovens, all of which have posed different electrical loads, which could be a challenge to upgrade. And then finally, in the cold climate example, this is sort of similar to my house, but not nearly that large. You have a large boiler with steam radiators, et cetera, et cetera. One thing you may have noticed, and actually all 4 of these scenarios, if you've been scanning the features in this box, is that all of these home scenarios have an electrical panel ranging from 30 to 100 amps, which can make it really challenging to electrify all the loads that you would find, particularly in this cold climate home where you might have a lot of resistance heat being used or need higher end heat pumps, for example. So phase 1, the concept paper, how to apply and what to submit. So those scenarios are, sorry, I'm getting lost here. So yeah, previously those scenarios are what American Made has provided, and participants are free to pick and choose and try different combinations. But what's important, and again, I just want to make sure this is iterated loud and clear, is that in the concept paper, and this is part of what to submit, the concept paper, there will be the scenario in which the demonstration will be executed. It should be there to make it past phase 1, and it has to be very specific. So next, how to apply and what exactly to submit. So applications are actually being accepted right now. Like I said, they've been accepted since last December, and the deadline for the concept papers is March 8th. So we're coming up on that deadline, but not too far away, but not a ton of time. And you'll be submitting those on the HeroX website. So this is just a screenshot of the HeroX site for this particular challenge. I'm sure you're all very familiar with HeroX, otherwise you wouldn't be in this Energy Tech Up competition. But on this page, again, under those resources, I believe are the full rules, this presentation that I'm giving to you right now, plus a video, a longer version of this presentation that's like an hour long, that goes into greater detail. And again, the purposes of me sharing this today is just to give you a quick flavor, a quick teaser of what this could be. So what to submit? First, you're going to be submitting a 1-page summary PowerPoint slide. The slide should just be an overall picture of what you're doing. And note that this slide will be public, so don't put any proprietary information on that slide. Next, you'll be submitting the concept paper itself. And so this is the meat of phase 1. It should be up to 3,000 words. And really get into the detail of the technology you're proposing to help make home electrification easier. This will also not be public. This will not be public. And then lastly, also not public, you'll need to submit CVs for each team member of your team. And then lastly, this is not required, but always helpful, are letters of commitment or support. So the concept paper, as I've mentioned several times, there's a word limit of 3,000 words, and this is a hard limit. Judges will not read past 3,000 words just to be respectful of their time. So that's why that's there. Obey that word limit. In the paper, you're going to be identifying some specific housing scenario your technology will be demonstrated in. So one of the scenarios I described earlier, or it could be a different one. You just have to be very descriptive and specific. And then you should describe the current solutions for electrifying that home scenario. I'm sort of imagining one of those infomercials where they show something to be so hard and so messy and, oh, this is crazy. And then you show the solution that makes everything so much better, like the picture comes into color. You're basically doing that in this concept paper, but you're also being very transparent about the benefits and the costs of your potential solutions, the risks and barriers, et cetera, because the reviewers have to be convinced that you've accounted for everything before they can trust that you'll actually reach actual demonstration. And again, all this is in the rules. And here are the rules. These are found on the American Made Challenges website, as well as the HeroX website for this prize. And so what's next? You can follow the challenge on HeroX. You can read the rules, connect with ADL Ventures, who's helping out as well. You can get support from the American Made Network Connector. And if you have any questions, you could email me, but I would probably forward it over to buildingprize@nrel.gov. So if you have any questions, please email that email address with your questions. And then lastly, you'll want to submit by March 8th at 3 p.m. Eastern time. And so with that, I'll take questions. I'm being fully transparent. I'm not an expert on this prize. I was just asked to share this prize with the folks in the room, just because it might be something very relevant to your teams. But if you don't have any super hard questions, or if you have no questions at all, I will stop my share, and I'll give you guys just a couple minutes break before the judges return to the room with some results. And I am told that we just need a couple more minutes for the judges to make their final decisions, so hang tight. All right, hello, welcome back, everybody. We're sorry for that, not delay, but you guys were very, very good. All these presentations were extremely good, which made the judges, it made their jobs very, very hard. So that's a good problem to have. So as you all know, the 8 DOE technology offices are offering prizes for the best teams in their respective fields. And those offices are the Building Technologies Office, Geothermal Technologies Office, the Office of Electricity, the Office of Fossil Energy and Carbon Management, Office of Nuclear Energy, Office of Technology Transitions, the Solar Energy Technologies Office, and last but not least, the Water Power Technologies Office. And the judges did a great job in trying to figure out which of the teams. So obviously there's one winner, but we wanted to make sure that we offered and nominated teams for these technology bonus prize winners. So I'm pleased to announce the National Lab IP Licensing Tech Bonus Prize is going to be team number 2, Kelly Energy Innovators. So congrats. The Geothermal Technologies Tech Bonus Prize will go to team number 7, Lehigh University. So congrats. The Fossil Energy and Carbon Management Bonus Prize will go to team number 6, UD Flyers. The Nuclear Energy Tech Bonus Prize is going to go to team number 9, New H2. The Grid Enhancing Technologies Tech Bonus Prize goes to team number 4, UC Powerhouse. Congrats. The Large Power Transformers Technologies Tech Bonus Prize is going to go to team number 9, New H2. Look at that. And if we had the technology to do this, we would have a drum roll playing in the background. I'm pleased to announce the Mid-Atlantic final winner is team number 12, Direct Recycling of Battery Manufacturing Waste. Again, this was very stiff competition, which is why the judging deliberation took so long. But congrats to everyone. So just to do something a little fun, I'm wondering if everyone could unmute themselves and clap and see what kind of response we get, because I think you all should celebrate how great this has all been. There we go. And so something fun we would like to do, just because this is virtual and it's always fun to, be in the presence of others, and it's kind of hard to do that over virtual. We're wondering if everyone could turn on their cameras and we can grab a screenshot of everyone celebrating their time today. Shaban and Hannah, are you guys able to turn on your cameras? Not to put you on the spot here, but
I think we can go ahead and everybody can wave and we'll take some screenshots. Yay! Thanks, everybody. You did a great job.
Yeah, thank you so much. Seriously, this means so much to the Scott Institute, and we really appreciate you guys doing this today. Very fantastic presentations. Congrats to all the Tech Bonus Prize winners, and of course, congrats to the Mid-Atlantic final winner. So thank you all. Best of luck, and have a great rest of your day.